Hey everyone, welcome to the first video of our image processing with OpenCV and Python series. In this series, we'll start from the very basics, understanding what an image actually is, and go all the way up to real-time face and object detection. If you have ever wondered how computers see things, how your phone unlocks with your face, or how AI identifies objects, this is exactly where it all begins. To truly understand image processing, we must first understand what an image really is. At first glance, an image looks continuous, but in reality, it's made up of tiny dots called pixels. Each pixel stores, colors information as numbers. Yes, just numbers. Let's start with a black and white image. So, let's take a black and white image first, and each pixel can be represented by a single value from 0 to 25. 0 means completely black, and 255 means completely white, and the numbers in between represent shades of gray. Now let's see a practical photo in Photoshop and see how these blocks and pixels are created. Okay, so here we can see there is a black and white image. So first, looking on this picture, it may look continuous, like there is no edges like that. But if I zoom this enough, you'll see the whole image is made with small square boxes, which we are calling that pixels. So let's zoom this photo first. And you can see that here you can see this value of this pixel is 0, and here the most widest one is 255, and in between there are different shades of from 0 to 25. More we are closer to 0, it's more darker, and more we are closer to 255, then it is much more lighter. So this is how small blocks and pixels created a photo, and if you zoom out it looks very much continuous. Okay, now what about color images? Color images are usually made up of 3 channels, red, green, and blue, also known as RGB. Each channel is like a grayscale image of its own. When combined, they form the full of color picture you see. Let's see a practical example in Photoshop that how a colorful photos is created by pixels. Now let's see a colorful image. So here you can see a colorful image. Now if I zoom this enough, you can see there are a lot of colors. Mainly there are 3 colors, but there are different values and they mixed up like that, and it may look continuous when we zoom it out. So after zooming, you can see there are different colors are here. This value is in between. It is for RGB, the mixture. So it's create all the colors possibly we need. As we know, these are the 3 basic colors. So when I have zoomed it out, you can see here. Okay, so this is how actually the pixels made our photos. So photos are nothing but some numbers. So each box have different numbers, and these numbers are created. As you know, the computers don't understand anything but only 0 and 1. So this is how these are created. So these has the values from, these are some, if you see there are some matrices we will use, and you'll see in further in our video that how actually we create colors in our digital systems computers. So this was a real example that how actually colorful image or black and white images are created. Another important thing is that each pixel value is stored in bits. For example, an 8-bit image means each pixel can have 2 to the power 8 equals to 256 possible values from 0 to 255. Higher bit-depth images can represent finer details and more colors. Now let's see, what is image processing? Image processing simply means performing operation on an image to extract useful information or enhance it. Just like we edit a photo to make it look better, computers do similar things but for analysis, recognition, or automation. For example, in medical imaging, it helps doctors identify diseases. In robotics, it helps robots to navigate. In AI, it's used for facial and object recognition. And in security, it's used for surveillance and motion detection. Okay, let's see, what is OpenCV? Now that you know what images actually are, let's move to the tool we will use to process them, which is OpenCV. OpenCV, or Open Source Computer Vision Library, is a powerful library that helps you process images and videos efficiently using Python. It can handle reading, editing, analyzing, detecting faces, tracking objects, and much more, all with just a few lines of code. Now let's see how we can install this OpenCV in our machine. So for this course, I will use here the Visual Studio Code. You can also use PyCharm, Jupyter Notebook, or even Google Colab, whatever you like. Welcome back to our OpenCV Image Processing with Python series. In the last video, we learned what an image really is, pixels, bits, and color channels. Today, we are finally going hands-on with real coding. You will learn to read images, save them, resize, crop, convert, color spaces, and even split RGB channels. By the end of this video, you will be comfortable performing basic image processing operations like a computer vision engineer. So let's start by knowing what actually is reading an image. So by reading an image means getting information from an image. Suppose we have an image here. It has a height and width. Now, each width have different pixels. So like this, right? And for height, we have like this. So when I do this, we get pixels. To know how many pixels we have in our height and width, we have to read that image using OpenCV. Also, the channels it has. So it means that is it 3-channel RGB or 1-channel grayscale? So you will know what information an image contains. So to know it properly, we'll now move in our real code in our terminal. So first we import OpenCV using ImportCV2. This gives us access to all image processing functions. Okay, now we'll read an image. To do that, we have to first write image equals to cv2 dot imread image dot dpg. Okay, so now you need an image here to read this. Okay, so I will have an image from downloaded from internet. So let's go to and pick an image from internet, like a picture. Suppose if we take this picture and if we download this, okay, and if we take it here in, and if we just rename this or we can just write the rename it image. Okay, now in our code we have, now we'll write that image jpg. I hope it should work. Now we have put the image here. Now I want to see what is inside that image and want to know what information does it contains. So I'll simply write here cv2 image show, and by cv2 I am read. Okay, so let's explain this line. So cv2 I am read the image from disk. We use cv2 I am read to read the image from disk. This loads the image into memory as a matrix of numbers. As I have previously mentioned in my previous video, that images are nothing but couples of numbers fitted in a matrix. Now then, cv2 I am show, it will display the image in a window. But if I run this code, then it goes very fast. So we have to wait for a moment to see what does it have. So if I write here cv2 dot wait key, when I'm giving here the value 0, it will wait for infinitive of time. If I give here 5,000, means 5,000 milliseconds or something like that. So I'd like to give it 0 to stay for a long time. And finally, I'll use your cv2 dot destroy all windows. So it will help to reduce the memory use. So now if I run this, you can see the image here. So this is the image we have created. Okay. Now let's move to our next section of this video, is saving an image. Okay, so how we can save an image? So we have already read that image. Now to save it, what we can do or write it, you can simply write cv2 dot I am write. Okay. Now what it will do, it will simply write the image back to the disk. So I can write it in a different name, suppose output image.png.image. Okay. Now if I save this file and run it, you can see that output image.png, a new image is created. Did you see that? So this is how simply we can do that. Now let's move to our next section of the video, which was image attributes. So what actually image attributes is? Image attribute means finding the shapes and sizes. Okay, shapes, sizes, the actual value of the, I have previously mentioned at the beginning of this video, the width and the height. So for these things, we have some code to do that, and let's see what is it. So let's move to the coding. So what we can do here, we can know the shape of the image. Okay, so let's comment out this, and okay, now I'll write here that print. Okay, so by using type, you can see what type of image, what type it contains. So it's a numpy array. Okay, now I'd like to give here, and if I write here print ng.shape, it will give me the shape of the image. So I'll write it here. Now you can see the shape of the image is 183, 275, and 3. So what it actually means? So this information gives us that the width is 275 pixels, the height is 183 pixels, and it is an RGB image. This is why it is 3-channel. So this is height, this is width, and this is channel. So if I show you some more information, like we can simply write here print height. So if you write here height image shape.0, it will only show you the height of the image. See, 183. Now if I write here print with image shape 1, the value is 1, then it will show you only the width. So this is how we can find out the shape of an image. Now if I want to see the image channels, now you can see that the channels 3 is 3-channel image. Now if I want to see total pixel size, it is also possible to say by print total pixels and size. Now if I print this, total pixels is 150975. Do you know how this value has came from? Okay, so this is the multiplication of 183 with 275. If you do this math, you can find out this answer. So the image we have here is created with total this amount of pixel, means single box. If I zoom it, you can see here single tiny blocks which are pixels. So this amount of total pixels are here in this picture. I hope the concept is clear now. Okay, now let's move to our next section, which is resize an image. Okay, so first I would like to comment out this thing. Or I can just simply remove this. I really don't need any other file longer. Okay, so what is about resizing an image? Suppose you have a task to resize an image. Like if I show you, okay, suppose you have an image like this. Okay, so suppose you have an image. Now, for a particular word, you need to crop it. Suppose I need to crop this image like this. So how did you do that? So behind this process, coding is behind in this process. So here I'm making this in size bigger, smaller. So according to our need, we need to resize images. So when I'm increasing this, the pixels are growing, and when I'm decreasing, the size is decreasing as the pixels. So this is what we do when we need to resize an image. So if I show you with some coding, you'll understand it clearly. First, we have to change the height and width of the image we have. So I would like to do that. If we have fixed the image size to like, and suppose we have the fixed sizes image, which is this, and let's see what happens if we give some random values here. Now I want to scale this image like this. Okay, so what I have did here, we can use scale factors fx and fy. For example, we have used here 0.5, 0.5, so that the image reduces 50% of its actual size. Now, I really don't need this thing to use, so I'll just simply run this, and if I show you CV on show scaled, okay, so it becomes more smaller. If I compare you with the real one, the CV2 and the okay, so let's change this. Now if I show you, if I run it, and you can see, okay, so this reduced 50% of its own size. So now let's move to our next section, which is cropping, or ROI, region of interest. So cropping is called ROI, region of interest. So we slice the image like an NumPy array. First numbers are rows, second numbers are columns. So we are cutting a rectangle from the image. So let's try this. We can simply delete these things, and this also. Okay, so what we'll do here, we'll crop by using crop equals to image like this, and show cropped image. Now if I run this file, okay, so if I change this, okay, now if I run this Python file, you can see the image is cropped. Now here is showing much more than I expected, because we give more value than the pixels we have. So if I run this file again, you can see the picture is cropped, and the main thing is you have to put here the real height and width, what we have already got. Okay, so this is how you can crop an image, by slicing the pixels or rows or columns from near the original size. Now let's move to the next section, which is color conversion or channel conversion. So if you start this, okay, so we have already written the image. Now to change its channel from RGB to gray, so here we have written BGR, which is blue, green, red, to gray color. We can use this, and then if I run this code, you'll see now the picture is on gray image. Now if I write this, that I'm right. Now if I print this, you can see the gray image. We got a gray image here. We have made it in one channel, in gray channel, and then we saved it. Okay, now if we want to convert this into PGR to RGB, how would you do that? To do this, what we can do here is RGB. So write RGB equals to CV2 dot CVT color image. Okay, then CV2 I'm show. Now if I run this, Okay, now you see the CVT. Now if you run this, you can see here that BGR is converted to RGB. Now you may ask that what actually this thing is. So it is actually the blue color is converted to red and the red converted to blue. If I do side-by-side comparison, it will be easy for you to understand what actually is happening here. So I'll simply do cv2.imshow original image. And now if I run this code, okay, and this one, now you can see the red section become blue and the blue section becomes kind of reddish, right? So this is how you can make a filter, right? So this is how we can convert different channels from one channel to another. Now we will move to our next section, which is splitting channels. So splitting channel is, okay, so I'd like to exit it to this one. Okay. Now to splitting image, I will do here B G R split image CV2 channel B, no, channel C. Okay, so now we'll split channels in blue, green and red in 3 different channels, single channels. So now if I run this, you can see 3 different channels. So it is having it is the blue channel, the red channel is green channel. So it is marking the red channel. So this area is red channel, green channel, and blue channel. So this is how you can show different single channels. Okay, so now let's move to next. Our topic is merging channel. So now you can also merge channels like cv2.merge is, and you can simply write cv2.imshow. So if I run this, after merging, you get the actual image. See that? We merge the 3 channels and our actual picture is again merged. Okay, so this was the video about some simple operations using OpenCV for image processing. And now you can read, resize, crop, and manipulate images using OpenCV and Python. These are the core fundamentals of image processing. In our OpenCV Python image processing series, we learned how to read images, resize them, crop them, and apply transformations. But today, we are moving into something more creative and powerful. We'll learn how to draw shapes directly on images, create masks, apply bitwise operation, and blend multiple images together. These techniques are used in face filters, augmented reality, logo overlays, object detection, and photo editing apps. So, open VS Code and let's start coding. Okay, so let's start with the simplest drawing, a line. Think of this like drawing with a digital pen on a canvas. In OpenCV, we just specify the starting point and ending point color and thickness. First, we need a blank image to draw on. Then we use the cv2line function. So to start this, I'll first import cv2. So which it is the OpenCV library you already know. Then we'll import numpy because images are stored as numpy arrays. Now we'll make an canvas. Okay, so we'll create a blank image using np zeros. So let's write image equals to np dot zeros, and I want that the height and width of that canvas or the image should be 500 and 500. And I want the channel of this image is 3 channel. So I'll write here 500 is the height and the width, and the channel is 3. And here we'll also write that comma d type means the data type is d type equals to unit 8. So the d type unit 8 means the pixel values from 0 to 255. Then now the canvas is ready. So we can write a line on this canvas. So to do this, we have a function called cv2line here. So cv2.line. So it will create a line where it will create inside the image. So I'll write here img. Then we need a starting point from where you want to start the line in your canvas. So the axis point, I would like to give here 50, 50. So it means from the x-axis or from the y-axis, both the distance is same. It is 50 and 50. Then the end point, that where you want your line to end. So I want it a straight but long x-axis to 400 pixels, and I would like to give here 50. And I can like BG. So if I want this change the color, you can use the color by using this. So let's make it to 5500, and then the thickness of your line. So I like to give the thickness 3. Now if I write cv2 dot show line image cvut and cvdestroy. Now if I run this code, you can see a line is created. So why this color is blue? Because we know the values is B, G, and R. So B means blue. So 2555 means we're having here the blue color, and 0 and 0. So we don't using here the green and red color. So if you want to change this, suppose you want to move that more, you need more on the right side. So what we will do here, we'll increase the value of this. So if I give here 500, it will go all through the end of the canvas. Now, if I run this, you can see it touches the edge of our image. So I hope you understand how we can create a line. Now, if you want to change the angle, you can change the value to 220. So if I turn, you see, because it creates an angle. It's not a straight because it's 50, 50, and this value isn't the same. So if I change also these values, you can see other things. So now the end point move further. So this is how we can create lines by using OpenCV. Okay. So now let's move our next topic, our next code. So we'll make here an rectangle using OpenCV. So how we could do that? So as usually, first we need to create an blank image, np dot zeros, and like that. Okay, so we can write here the type. Okay, like this. Now for an rectangle, what we'll do here, the cv2.rectangle draws the shape. So first we have the image, then we'll write here cv2.rectangle, then img. Okay, so let's send this to img. Then we'll write here 100, and then I'll write here 400, and this. So this is the top left corner values, and this is the right side lower bottom corner view, bottom corner line, sorry. So by changing this, you can change the distance from your canvas you have taken, that where it will start creating that rectangle. So now if I complete this code, see it dot I'm show rectangle image, and then okay. Now if you run this, you can see a rectangle is created. So if you change these values, this line and this line will move. So let's see how does it happen. So if I made this 0, there won't be any distance from the canvas, and it will touch the edges of your picture of the canvas. See, this moves there. Now if I increase this distance, this will go farther on the right and the bottom of your canvas. So if I make this 500, see, this moves more further. And if we increase these values, it will create more distance from the canvas, from the left side and the top side. See, that increases the distance. So this is how we can create a rectangle in our OpenCV. Now let's make a circle. Just like these processes, we can also make circles. So to make circle, we need to write here first. Okay, so we took the same canvas. We have to just change this to cv2 dot circle. Then we have this. Okay, so these 2 points mean the center on your axis. Like, you know what a circle has. So suppose this is the canvas that you have, then this point is what we are mentioning here. If we reduce the values, it will somewhere here or here. Then we need a radius to make a circle. So this is 100. So if this is the center, the value of x and y, then the radius, suppose this is the radius, which is 100, then it will create an circle around it like this. And we have given here value in b, g, r, so it will be a green color, and we give here a -1, so it will fill the image. So if you run this, it will be much more clear. Okay, sorry, I just forgot to give here the cv2.imshow. Now, if I run this, you can see a circle inside the box. So if you want, it shouldn't be fill. You have to just change the value to a positive value, and it will become only the thickness of the circle, like this. Okay, now let's move to our next topic. So we have showed you how to create rectangle, line, circles. Now, how we can add text in our images. So to do this, you have to move this, and you have to write here cv2 dot put text, and we want to put text on our image. And what do we want to write? So we can write that, hi, this is Prism Byte. Then we can fix that where we want to place the text in our canvas. So suppose I would like to give it the value as 20 and 250 is good. Then we have to choose the font. So there are a couple of fonts here. So we can take this one, and we can also select the colors, the size of the fonts, and the thickness. So if I give here just as it is, and now if I write here CV to unshow, then you can see if I run this, hi, this is Prism Byte. It is written. So if I change the value to 2, the size decreases of the text. Also, if I decrease this, the thickness will also decrease. See? And if you want to change the color, you can simply do by doing this. See, the color is changed. So this is how you can add text on your images. Now, we'll move to another important topic, which is masking. It's a very important topic. So what actually it is? Masking means selecting only specific areas of an image. Imagine covering everything except one region with paper. Only that region is visible. That's exactly how masks work. So to do this, I will take here an image instead of creating any canvas or any blank image. I'll write here cv2 dot I'm read, and instead of this, I'll write here we have a picture. A file I have already taken here, and this is the picture. Right? Okay, so you have to put this picture here, and then you have to write the name here. Now to mask, I'll write here cv2 dot. So it will circle. The area I want to cover is circle, using circle. So circle. Then I'll write here mask. Now the axis where it will start, the center of the circle. Okay, so I have missed one thing. So first we have to write here the mask to create. So to do this, I have to write here mask equals to np dot zeros image shape dot. Okay. So what does it mean here? So this 2 means it has only height and width, no color channels. Then it will draw a white circle, and white means visible. Now if we come back to here, this mask will 150, it is the radius, then it will fill the circle. Then in results, what we want here to CV2 bitwise and so bitwise and keeps only the white region, so only the circle area remains. So I'll show you the original image and also the mask image so that you can understand what actually is happening. So only this portion is visible here from this image. So what we did here actually, we created a circle which is filled, and then we took the pixels or information only this area according to this circle. So this is a very important concept, and we need to use here in many tasks or many important applications. Now let's move to our last topic, which is image blending. So image blending means combining 2 images with transparency. Like Photoshop layers, it is very useful for overlays and effects. So to do this, we need to take 2 images first. So I have already downloaded 2 images from internet here, this and this. So this is an image of a forest and this is an image of sea and sky. So I want to blend these 2 images. So to do this, I'll do here. First, let's remove this and write here image 1 equals to cv2.amrid and then picture.jpg and image 2 equals to cv2.amrid picture2.jpg, and we need to make this do 2 pictures in equal sizes. So what I will do here, image 1 equals to cv2.resize. We have already covered the resize part in previous lecture. So image 1, comma, so we want 400 and 400 pixel size from the original one, and same for the second image. Now for blending, what we'll do, we'll write here blend equals to cv2 dot add weighted image 1. So let's start with taking 50% of each images. So to do this, I'll write here 0.5 from first image, and from second image, I'll take 50% also. So 0.5, and let's write 0. So what is actually happening here? This weight means the percentage of each images. Now, if I write here cv2 dot, I'm show when image blend. Now, if I run this, you can see the both images here, the sea and the grass. You can both see here. Here was the sky and the forest. Both images are blended. If I show you here, this was the only image with sea and the sky, and this was the image of only forest with trees. In our result, what we got here the both. So what we have learned here, we can blend two images like this. Now, if I change these values, if I do this 0.7, it means the first image has more weight. It means it has more value. It will add more than the second one. So we have to reduce it to 3. Now, if I run this, let's just close it. If you run this, you can see the first image was of forest, so it is now much more visible than the second one. So this is how we can create over layers like Photoshop and two images with transparency. Hey, welcome back in this OpenCV Python image processing series. Today we dive into image transformations and effects, how to move, rotate, scale, flip, and even change the perspective of images. These operations are code to computer vision using robotics, augmented reality, and object detection. By the end, we'll build an interactive transformation viewer where you can control angle and zoom in real time. So let's start with our first topic today is the translation. So translation means shifting an image like sliding a photo on a table. Pixels move, but their values stay the same. So let's start this. First, as usual, I will write here import CV2, then import numpy as in p. Okay, now I have to select an image here, which one I will translate. Now, by doing this type of translations, first I would like to select an image equals to cv dot im read, and then here I have some images, so I can use this one. So right here the picture jpg, so picture jpg. Okay, now what I will do here is for translated I need the translation matrix. So to do this, I'll write here np numpy dot float 32, and then I'll write here now the 1, 0 tx means 100, and then 150. Okay, now so here it's called it is what it will do, it will shift right the image by 100 pixel, and this will shift the image to the downside. Now what I will do here is translated equals to cv2 dot warp affine, and now the image we have, and we'll apply here the translation, and then I will just simply write here image shape. So this is the row and the column. So now after this, what I can do here, the cv2 install windows. If I run this, you can see it's moved here. Okay, now Now you can do this type of thing before we can define the rows and column like this. So here's another way to do this. You can write here row and column image shape. Now what I can do here is, instead of all of this, I can just simply type here column and row. So now if I run this, you can see the image is shifted or translated. Okay, now we'll move to our next topic, which is rotation. We'll rotate an image. So rotation spins the image around the center point, like rotating a picture frame. So first I will write here cv2, then we will write here image equals to cv2.imread, and then picture 2.jpg. Now we'll find the center here. So the center will be which is the column of our picture. Okay, so before that we'll define the rows and columns. So rows and columns equals to im image dot shape. Now I got the rows and columns of this image in a matrix form. Now I'll find out the center of this image, which is center equals to columns / 2 row. Now I have the center. So now what I will do here, I'll define aim equals to get rotation matrix 2D and center 45, 1. So what we're doing here, 45 means it will rotate at 45-degree angle, and 1 is the scale. It means I'm doing here no zooming. Now after that, rotated equals to cv2 and columns. I'm sure the rotated image with key, and let's run this. You can see the image has rotated. So this is how you can rotate an image. Now you can change this, like if I want to rotate it at 90 degree, I can just simply change here and run this, and you can see the image has rotated 90-degree angle. Okay. Now let's move to our next topic, which is scaling. Okay. So we're taking the same image. Now make a variable scaled equals to cv2.resize. Now image, none, fx equals to 1.5, fy equals to 1.5. Okay, now small equals to, okay, now what we can do here is, okay, so now what I have done here, that fxy and fxx, they're the scale factors. So when the value is more than 1, it is zooming in, and when the values are below 1, it means zooming out. So what I'll do here is scaled. Now another one is zoom out, and cv word key, and destroy the all windows. Now if I run this, you can see two images. This one is the zoom one, and this one is zoom out. This is the small one, this is the scaled one. So this is how you can make an image scale bigger, and this is how you can make smaller. Okay, now let's move to our next topic, which is flipping. Flipping creates a mirror effects, horizontal, vertical, or both. So let's see how we can do this. So first we'll make here h equals to cv2 dot flip image, and then v equals to flip image 1, and if I go here for both, this is for both, for horizontal and for vertical, for both I have done this. Now cv2 show here. Now if I run this code, you can see here this is the vertical flip, this is the horizontal flip, and this is both. Okay, so what happened here? This is the vertical flip, a mirror on the right side. This is the horizontal, is a both flip, and this is the horizontal flip. So this is how you can flip an image. Now we'll move to our next topic, which is affine transformation. Affine transformation lets us skew or stretch the images. Parallel lines remains parallel. So how we can do that? Let's start with this, and first we have to import here numpy, import numpy as np, and now we have here the pts equals to np dot float 32, and we can make this kind 50, 50, and let's erase this, and we have the pds one, which is this, and then we can make here an aim equals to cv2 dot up cv2 dot get affine transform pds comma pds1, and we can write here affine equals to cv2 dot warp affine warp cv2 dot warp affine, and then image columns and rows. So I have to define here the rows and columns before that. To do this, I'll write here rows and columns equals to image shape, and we can write here 0, 2. Okay, I don't need this, so it's the image of shape, and I can write it here. After that, what we'll do, we'll just write here cv2, but okay, now let's see what actually happens here. Okay, some mistakes I have done. Okay, sorry. So what I have to do here is columns and rows image dot. Okay, sorry, I made a mistake here. And now let's run this, and you can see the image is traced and also transformed. So you can see this is how we can do the affine transformations. Okay, now let's move on to our next topic, which is the perspective transformation. So perspective transformation changes viewpoint like tilting a document. So just like that, what we'll do here, we'll do some changes on this line. These 3 lines will be changed. So here what we'll do, we'll make it 0 and 0, and we'll make here the columns, calls, and then 0. We'll make it here rows. Okay, we'll make it here like columns, and we'll do it here rows, and here I'll do make it 50, and this one is also 50, and columns minus 50, and make it 0, and we'll do 0, 0, column 0. I will make here another row, which is okay. So we need 4 variable here. So what we'll do here is make another one where I'll 0, comma rows, and here we have 0, comma rows. So we can here 0, and we can put here the rows, and we can here the column. Okay, we don't need the minus 50. I have the columns, so that rows minus 50. Okay, now transformation, instead of affine transformation, we'll write here the perspective transformation. So let's write the perspective transformation, and now instead of verb affine, we will write here perspective. So perspective cv2.verb perspective image and we'll write here, instead of this we'll write here perspective. Okay, done. Now let's destroy save it to the destroy all windows. Now let's run this one. You can see the image has tilted. So now I'll explain what actually we have done here, that we have 2 points have taken. One is like you can see from this is the 0 point, and then the columns from the 0 side, and the columns is minus 50 pixels, and we took here the 4 sections so that we can tilt and also stretch the image. Okay, now let's move our next topic, which is image pyramids. So pyramids create multiple resolutions of an image, important for detection. So how we can do that? So for this, let's remove this one first, and okay, this one deleted, and let's make down equals to cv2 pi down image, then up pi up. I'm sure original, I'm sure down, and I'm sure up. Okay, now let's run this, and you can see this is the down, this is the up, this is original. So what we have did, we have created multiple resolutions of an image. So sometimes we need to blur something in our image, we need less resolution on the background but much more in the in front, so where we are standing. So this is how we can change the resolution of an image, or you can also change a particular part of an image. Now let's do our final project, an interactive transformation viewer. Let's build something powerful, an interactive viewer. You can change angle and zoom using slider. Okay, so how we can do that? So let's start from here. Okay, now first what I'll do, I'll make here a function def nothing x pass. Okay, now cv2 dot name window is transform, and then I'll make here cv2 dot create track bar, and I'll name it as angle. Okay, angle, and then I'll create here cv2 dot track bar scale. Okay, now while true angle equal angle cv2 get track bar pause angle transform, then the scale. Now rows column image shape, now rows column image shape. Now we need two rows column, then we need the center, right? So here is the center for the rotation angle, and then it's the angle and the scale, and we have warp fine. Okay, so what actually we'll do here is first understand how the rotation will work. So in before we have seen here, in case of rotation we give here the center, so we have done this here, an angle and the scale. So angle and the scale will be in the track bar, where the values are from 0 to 360 and the scale is from 1 to 10. Okay, now after that I can write here, and at the end we can write here cv2 desktop windows. Now let's run this and see if it still works or not. Okay, so this is the image we have. Now if you want to change the angle, by changing the value it will rotate, just in like your software we used in our editing. And for scale, as the value is changed, it will zoom in and zoom out. Okay, so this is how we can make the editing softwares, photography editing softwares, or anything you see in the mobile phones or Photoshop. This is the background and how actually images are transformed. So this was the video today, and in this video you learned how to transfer images using OpenCV Python from translations and rotation to perspective and pyramids. Hey, so today we move into one of the most important parts of image processing with Python: filters and enhancements. We'll study blurring filters, edge detection, thresholding, morphological operations. These are the mathematical foundations behind computer vision systems like face detection, medical imaging, and object recognition. So let's start with this. That first, as usually we all know that what image is a discrete 2D signal. So first, here is noise. So what actually noise is? It is the high frequency components in a picture. Suppose you have a picture and where the frequency gets very high, that point is known as noise. And edges. So what is edges? Suppose you have a picture like this, and I have to show you for a little bit. Suppose you have this picture, and what you can see, when there is a transition here, the values change rapidly. You can see that these values are literally different than this. So so by using this concept, we can identify the edges. Now, what is blurring? So blurring is basically we need the low pass filtering to suppress the high frequencies. So as we have mentioned before, the noises are very high frequency signals. To suppress this, we will use low pass filtering. So now let's move to what is convolution. Okay, so it is basically slide a kernel over an image and multiply the neighborhood pixels with weights and sum them and get a new pixels. So in easy words, think like that. You have a picture like this. Now these are the blocks of the pictures. These are the pixels. Okay, now these have different values. Suppose you pick this size, each have different values. So what we can do, we can average all the values and put same values everywhere, or we can give much more attention or importance to the center value, or there are other ways to do this. So this is how we actually apply the kernel to an image. Now first, about if I go about the filtering, we have the average filter. Now before going to this, I would like to explain the mathematical term here, that what actually it is meaning. So the I prime xy, it is the new pixel or new processed pixel that we're getting after applying the convolution or filter. Now here the IXY, which is the original image, so before the change. Now here the K, so what is K? So K is the kernel value at position ij, and what is I and J? It is the offset from the center pixel. Now what K actually is here, the K is how much pixels you are taking for doing the average. It can be 5 by 5 or it can be 3 by 3. So when it is 3 by 3, it means you are taking 3 pixels from the row and 3 from the column, like this, and you will average. If it is 5, then you will take more 2 rows here and more 2 columns, like this. So this is like a 5 by 5 kernel. So now what we have here, and after all this is the summation, and after all we summation all this and put it in our new pixel. So this is our first filter, which is the average filter. Here we are taking the kernel, which is k equals to 1 by 9. So the mathematical formula should be here is 1 by n square, and then as it is, it is 3 by 3. So when the value is 3, it's becoming 9. And here we have, now maybe there are some different different values we will put here after doing average. So every pixels contributes equally, which is simple smoothing. And the problem is here the edges get blurred heavily, as we are doing it averagely for each pixels without giving any weight. Okay, now let's see in our terminal how actually average filter look like. Okay, so here is an image. I have already written the code here. So here is the image we have put it, and we can simply just write here blur equals to cv dot blur image, and we're taking here the 5 by 5 kernel. And now if I run this code, you can see this is the average blurred, right? But the problem is, as we have mentioned before, the edges get blurred heavily. And this is the original image, and this is after the average blur. Now let's comment it out because we don't need this anymore. So we can comment it out. Now let's move to our next topic, which is the Gaussian blur, right? Yes. So here we can see that instead of equal weight, what we're doing here, we're giving much more importance to the center pixels. So suppose you have like this part of your picture, and what you want much more give value to this one. Suppose this one is 150, this one is 5, this one is 100, this one is 10, 8, or 300, 300 can't be, the highest value is up to 255. So 250, 200, 1 and 0. So what actually will happen, before that we used to average all these values, and then we used to put each the same value everywhere. But now we'll give weight to this value, and each value will be near to this value. So this is what is here we are doing in this calculation. So this is the gxy, which is the weight at position, and here is the sigma, which is the standard deviation, which actually controls the blur strength. And here we use the Euler's number and the exponential, and then we have the xy, which is the distance from the center. Now when pixels are near center, we have the higher weight, and the pixels the far from the center, we use the lower weight. So as we have mentioned, suppose there are a lot of pixels here, and what will happen here, from the center, what is the value of the center? Suppose this value is 15 and others, and so when the values are closer to this will get more importance. Okay, now why Gaussian is actually better? Because in real world, blur follows a normal distribution. Not they actually equally blur everything. Rather, we focus where we have to do much more blur or where we have to do the less blur. Okay. Oh, now let's move to our... Okay, so before that, let's see how actually Gaussian blur looks. So let's move to our terminal and see how actually Gaussian blur works. So I'll comment it out, and let's see the Gaussian blur. And if we run this, you can see this is the Gaussian blur. Now you can simply compare it with the simple blur, which is, where is that? It's an average blur. You can compare these two side by side. This is the average blur and this is the Gaussian blur. So what you can see, in Gaussian blur it's still blurred, but in case of this, everything were blurred used to in same way. And when you see these edges, those were blurred too much, but now the edges are much more visible than before. Okay, now let's move to our next topic, which is median filter. Now, what actually median blur is? So here, instead of averaging, what we do first, we sort the pixel values and then we take the middle value. So it does not blur the edges so much. So let's see what actually is. Suppose you have the neighbor pixels, which is suppose 10, 200, 15, 12, and 14. Then what it will do, the algorithm of it will sort it like this: 14, 15, and 200. So now how it will blur, it will take the median value, which is the 14. So it removes the extreme values. So for noise removal, it's a very great choice. And instead of averaging, we choose the middle value, which removes the noise without blurring the edges. So now let's see in the code how it's actually look like. So let's just comment it out, and if we run, you can see this is what actually median blur looks like. So this is the Gaussian blur and this is the median blur. You can see in case of median blur, it's much more clearer, right? A little bit of animative work if you watch it closely. So what is actually doing in each kernel, it has, suppose this as it is 5, so it's showing that how much it is the intensity of the blur. This is the kernel size. And in case of the Gaussian blur, we also took the kernel size. Okay, now let's move to our next topic, which is bilateral filter. So in case of the bilateral filter, what we have here, that we have this mathematical equation. So what we are actually doing here, we have a spatial closeness and an intensity similarity. What does it mean actually? It's meaning the nearby pixels matter and similar color pixels matter more. So here, this is the mathematical equation. So GS, it is equating the P minus Q, and GR is IP minus IQ. So, and what actually it does smooth regions and preserve the edges. It's a much more advanced technique for doing the filtering. So what it is named as bilateral because we are actually combining two weights here. One is for the spatial closeness and another one is for intensity of color. Now let's see in the code how actually bilateral looks like. Now if we run this, you can see. So this is the bilateral blur. So it's now much more animative if we watch it closely. It's much more animative than the others one. Okay, so this was about all the blur filters what we usually use in our OpenCV and other works. Now let's move to our next topic, which is edge detection. So in case of edge detection, what's the fundamental idea is edges are the rapid change in intensity. So we can find out by using the derivative. So when suppose the change, when the derivative is so much higher, the change of pixels is, suppose there is a change of pixels, but the derivative will be lower than this. Suddenly the derivative gets higher. So then we can detect here is an edge. And this is how actually computer identifies the edges. To do this, we have the formula here, or a Sobel operator, where the dx is the change in horizontal direction. So what does it mean? That if you have an image, suppose like this, and in the x-axis the change of pixel is calculated by this, and for this gy, what does it do? It calculates the change in the y direction. The intensity of the image suddenly increases the value of this. So this is how, using derivative, we can find out the edge. And finally, what is that? Now finally, what is that gradient magnitude? It is the gradient magnitude here. And here the large value means the sharp edge and small value means the smooth area. So edges are just places where pixel intensity changes rapidly. So now let's see how does it actually find out in OpenCV using these formulas in our terminal. So first we will remove all this, and for edge detection we can use this, then Sobel X, Sobel Y. This is the code we can actually use for seeing how actually we detect. And if I run this, you can see this is the Sobel Y. So what is actually here it's doing, it is finding out the differences where the intensity suddenly changes higher in the Y direction, and it is for the X axis where it changes high. So by combining these two, we can actually finding out a clear edge. Okay, now let's see the Laplacian derivative. Okay, so to do this, we have this mathematical formula here, which is del square I by del square I. So it is the Laplacian operator, and we are using here the second derivative, the rate of change of change. So before that, in case of this one, the first Sobel, we use just the change, the where it's supposed from 50 where it becomes 60. Now we are actually calculating that where the change is actually the rate of change of change. Suppose before change was at 5 rate, now where the 5 rate is changing much more, is it going higher or lower? So it is much more, it detects where intensity changes sharply in all directions. So Laplacian looks at how fast the change itself is changing. So it's much more complex and much more advanced for finding out the age. So let's see in the code how it's actually work. So for do this, I'll heal it, and if you run this code, you can see this is what actually Laplacian works, and this detects all the changes where it's changing. Now the most important topic is the Kenny edge detector. So it is actually the multi-step math pipeline. So here the algorithm steps are first the Gaussian smoothing that we have already learned. So the Gaussian smoothing, we have an image and we apply here the Gaussian smoothing. Then what we do, we calculate the gradient that we have already learned before here, how we actually doing the first derivative. Then after that, the non-max suppression. So what it actually do, it keeps only the strongest edges and it remove the thick edges. Okay, and what is the double threshold? Okay, so threshold is doing, suppose you have the like what you can find out that how much it is. So it is if it's strong, if it will be strong if G is higher than your threshold value what you have set, and it will be weak if the value of G is between your threshold values you have set in your code. So what actually it do, there is edge tracking, means it keep the weak edges only if connected to strong edges. So it only keep the weak edges when it is connected to strong edges. Now Canny is not just an algorithm, it's a pipeline of multiple mathematical operations working together. Now let's see how it's actually look like in our code. So what we can do here, we can just write here Kenny equals to, and okay, now if I run this, you can see this one is Kenny edge detection, and you can see the instead of Laplacian, the Kenny edge is much more very good clear result it's giving us for the edge detection. You can clearly see this was the home, this is the bridge, and this is the sky, and this is the sea. So everything is actually detected differently, as we have truly applied so much algorithms here. Okay, now let's move to our next topic, which is the thresholding. As we have already mentioned this, so what is the thresholding or threshold logic is? So actually we separate the object from background using a simple decision boundary. So what it is, now we have two thresholds, like weak lower, which is the weak edges, and upper, which is the strong edges. And here in thresholding, we have the I prime, the value can be from 0 to 255, and t is the threshold if it is greater than ixy. So for simple thresholding, we use this code. So here 255 is the max value and 127 is the threshold value. And how actually the simple threshold works, now we move to the code and see how actually its work here is. You can see if I run this code, here is a simple thresholding. So simple thresholding can be in many ways tried. We have the binary inverse, the truncate, the 2-0 and 2-0 inverse. So these all are the simple threshold, but with some differences. If I run this code, you can see, so this is the binary threshold and this is the 2-0, this is binary inverse. So it's actually the inverse of this one. So where it was white, it becomes black. So it is 2-0 where we detected the zeros, and this is the 2-0 inverse, the inverse of this one, and we have the true and C actually. So this is how we can apply the simple thresholding. Now if I move to our next, which is the adaptive threshold. So what actually adaptive threshold is, that threshold changes per region, and txy, which is mean of the neighborhood, and here what we have, we minimize the intra-class variance. So automatically it finds the best threshold. So the sigma and the weights are automatically detected, and then we use it to find out the best threshold value. So let's see in code how actually the OTSU method works. Now to do this, we just comment out this. So this is the code for OTSU method. So the blur equals to Gaussian blur, then OTSU dot threshold blur, this is Gaussian blur, then 0 to 225, and threshold binary plus CV2 threshold OTSU. So we have applied here the two threshold here, and now if I run this, you can see this is the original image and this is the OTSU threshold. So this is how we can actually convert into black and white, and also find out the difference between the edges, and actually we can change it from the background. I have forgot to show you the adaptive threshold. Sorry for that. Let's move a little bit backward. I forgot to show you it in our code. So here we can see the adaptive Gaussian and adaptive mean. So this is the adaptive Gaussian and this is the adaptive mean. We have used, first we did the Gaussian blur, then use this adaptive threshold, and this the after the Gaussian the mean blur, we use the adaptive mean. So this was the topic we just missed. And okay, now let's move to our next topic, which is the morphology. So what's actually the morphology is, it's actually using a structuring element to modify shapes. So here we have the erosion. So it actually shrinks the objects, and here is the code for that. And we have the dilation, so which actually expands the regions, and we have opening, which actually removes the noises, and we have the closing, which actually fills the gaps. And these are the morphology on OpenCV. Now if we see it in the code, what we have here, just the displaying the all the dilation operation here, and we'll just comment out before this one, we'll comment it out, and we can see only the morphological part. So in this code, you can see here the kernel structure. We take the 5x5 kernel, then in erosion, CV2 erode the threshold binary, then the kernel, then the iterations of 1. Then for dilation, CV2 dot dilate, threshold binary, kernel iterations 1. And this is how we can apply all this, and we can just, so we have all the opening on erosion and black hat, top hat. We didn't discuss that, but the gradient, the closing, the dilation. So every kind of detection, the morphological operations, what you can apply here. Welcome back everyone. Today we are going to learn one of the most powerful concepts in computer vision, which is contours. By the end of this video, you will know how a computer identifies the outline of an object, measures its area, finds its center, recognize its shape, and even distinguish between circles, triangles, and rectangles. So, what is contour? Imagine I give you a coloring book. Before you color any object, the first thing you notice is its outline. That outline tells you where the object begins and where it ends. A computer works in a very similar way. Instead of understanding an entire object at once, it first identifies the object's boundary. That boundary is called a contour. Now let's understand by using real-world analogy. Imagine standing on a rooftop looking down a football field. You cannot clearly see the grass. You cannot see every player, but you can easily recognize the football field because of its white boundary lines. Those white boundary lines are like contours. Another analogy is, imagine a country on a map. How do you know where the country ends or starts? Its border. The border is its contour. The land side may contain rivers, cities, forests, and mountains, but the contour only describes the outer boundary. An image works the same way. So, let's understand the mathematical definition of contour. A contour is a collection of points that lie on the boundary of an object, where C equals to, you can see here, the xi, yi. So what actually does it mean? So here C is the contour, the complete boundary. The curly braces means a collection, just like a Python list, and the xy coordinate of one boundary point. And here I means the index number, like 1, 2, 3 from end point. Now, how does OpenCV find contours? OpenCV uses contours following algorithms to trace connected boundary pixels. It starts from the one boundary pixel, follows the edge until it returns to the starting point, and stores every boundary coordinate. These stored coordinates from the contour. Now, why do we need contours? Many beginners ask, why not just process the entire image? This is a very good question. Imagine you have a 4000 by 3000 image. That's mean you have 12 million pixels. Suppose the object occupies only 5% of the image. Why process all 12 million pixels? Instead, OpenCV only processes the object's boundary much faster, much less memory. Now here are some applications like medical imaging, self-driving cars, OCR, scanning your PDFs, robotics, manufacturing, agriculture, face detection, satellite imaging. Now, there is a confusion about edge and contour, but edge is only an intensity change. So what actually it does, it calculates the intensity change, but in case of contour, it's a complete closed boundary. Think of edges as individual pencil strokes showing where brightness changes, but a contour is what you get after connecting those strokes into a complete outline of an object. Now, before doing contour calculations, we do some thresholding. So, why does we do that? Suppose your image contains shadows, textures, colors, reflections. OpenCV gets confused. So we simplify the image from original to the gray, then we blur it, then we threshold, then we convert it to binary numbers, then the contours. Now the computer only has to distinguish between foreground and background. So now let's move to coding and see how actually we use contours in our programming, in our coding. Now let's open your terminal and start coding. So first we will try to find the contours. So to do this, we first import CV2. Then we need an image to create here. So it actually reads the image. So we did use to cv2.imread, which will read the file. And here you can see I have some pictures out there. So let's pick something from here. We can take this one, I guess. Okay, so in our code, we can write here picture 2. So right here the name picture 2.jpg. Okay. Now we have to convert it to the grayscale. So when we convert it into grayscale, what does it? From the BGR image to a single channel grayscale image to simplify the shape analysis. So we'll just simply do it here, and after that we'll apply threshold, which will convert the grayscale image to a binary image, and the pixel above 127 become white and pixels below it become black. So let's apply here threshold. We write it like this. This equals to cv2 dot. Okay. Now what we will do here, we'll find the contours. So to do this, we need to detect the bound. So what it will do, it will detect the boundaries or outlines of shapes from the binary image. Then we'll apply here cv2 rated 3. Okay, so first apply it and then see what is it. So if I do it here, you can see the RETR external. So, and there is also, we can use here the RETR3. So there are many modes, we'll learn it later, but for now we'll use here RETR3. So what actually it does is it retrieves all contours and creates a full hierarchy, a nested shapes. And here the chain approx simple which compresses the lines to save memory. Like rectangle is just 4 points. Okay, so after that, what we'll do, we'll move next, and we need here to print it. So we'll print the total count. So we'll write here print, then number of contours found. So we'll write here numbers of contours found equals to, then we'll write the length of the contours we have. Okay, like this. Then after that, we'll display the image. So now we'll CV2 for display. I'll write here I am show, and then the name will be binary, and it's from threshold. And after that, we'll use here just wait keys like CV2 dot wait key, and we'll destroy all the windows so it will save our RAM. Okay, and let's see what actually is it works or not. Okay, if I run it, okay, you can see here it actually worked. You can see the borders of and every spot here, every shapes. So it is the way you can actually find the contours of an image. So if it was as it is a complex image, there are many shapes you can see. Like here is almost rectangular shapes, and there are different irregular shapes. But if it was a proper regular shape, you will be able to find circle or square if there was it. But for now, you can understand that how actually contour works. Okay, now let's move to our next part. What we will do here, we will create another file, and here we'll draw contours. Okay, so to do this, we'll simply again write here import CV2, and then we'll write here image equals to CV2 dot imread. If we again use the same picture here, and then we'll same way use the gray conversion, so it would be like this, and after that we'll apply the threshold as we used it before. Okay, then we'll use the contour find. How we use the contour finding, so we need to use here contours hierarchy, and then we'll use our output equals to image dot copy. Then here we'll draw contour. So draws here, the draw contour is a function. What it will do, it will draws the detected shapes outlines onto the output image. So as first we have our main image, then according to that image, after finding the contours in a different canvas that we have copied the image here, and the output will draw it. Okay, so if I write it, what this means actually, here 02550, it actually is meaning it will be the green color that we are going to do the border around the outlines of the contours. And also here you can see the -1, it actually specifies that all found contours should be drawn. And here the another thing is that the sets the thickness of the drawn contour line to pixel, like here is 2, so the line of the thickness will be 2 pixel. Okay, so after we have completed it, then we'll go to the next part. here we'll display the result. So you simply write cv2 show contours output, then we'll use cv2 dot wait key, and then cv2 dot okay. If you run this, you can see that here we have actually draw the contours we have extracted from this picture. So this is the outline we made here. So this is how we can actually draw contours when we need it. Now we'll move to our next topic. So for that, we'll create another file. Name that file as contour retrieval mode. So like the rm.py. Okay, so what actually it's, so to understand the modes, we'll first simply start as we're doing. So I'll just copy paste it from here like this and put it here. Okay, here what we'll do, we'll show you the how actually the modes work. So here modes equals to, okay, so there's 1 2 3 external 1 2 3 4 modes out there. So okay, so now explain each one of this. So what actually RETR external works? So it retrieves only the extreme outer contours, ignoring nested inner shapes. So you will use in your contour function according to your situation. So what actually you are wanting from it. Now if you use this RETR list, what it will do, it will retrieve all contours without establishing any parent-child relationships or hierarchy. And if you use it RETR CCOMP, which will does that retrieves all contours and organizes them into a two-level hierarchy, outer boundaries versus holes. And if you use it, as we have already used this, what it does, it retrieves all contours and reconstructs a full hierarchy of completely nested shapes. Okay, now we will here create names equals to, so we'll create a list of strings that matching the retrieval modes to use for console prints and window titles. Now what we'll do here, we will iterate through modes, then loops through both lists simultaneously, pairing each retrieval mode constant with its corresponding text name. So what we'll do here, we'll write here for, then mode zip modes. Okay, then what we'll do here, we'll find the contours, detects the shapes using the current loop's retrieval mode, then we'll threshold copy it, then it will pass to preserve the original binary image data across loop iterations. And here cv2 chain approx simple compresses the segments to save memory. Okay, then so if I write here contours is like this hierarchy threshold. Okay, then what we'll do here, we will write here the output image copy, then we will draw contours. Okay, so to draw contours, and then it draws the detected shapes outlines onto the output image and copy in green with a thickness of 2 pixels. And I have already told you that -1 specifies that all found contours under the current retrieval mode shown. Okay, now write this, and lastly we'll print the result. and CV32 destroy the windows. Okay, now if you run this, you can see here okay. So now now when we use this, you can see this is a little bit different, and now we captured much more contours than before. Okay. Now here we can do it much more better way that okay, so if I do this, you can see here this is the list one, this is the external one, this is the comp one, and this is the tree. So both are a little bit different, as you can see here. This is the external mode, this is the red comp mode, this is the tree mode, and this is the list mode. Okay, so okay, now we'll move to our next topic, which is shape approximation. Let's see how we actually do that. So let's make a new file, name that shape approx.type. Okay, to do this, so first part is always the same, so I'll just copy it from here until this part, and paste it here, and after that what we'll do here, just output image copy. Then what we'll do here, we'll look through contours, so to iterate through every individual shape contour found in the image. So what we'll do here is for cnt in contours, and then we will calculate the perimeter, which computes the total perimeter or arc length of the current contour. Then the true I indicates that the shape is assumed to be closed. So perimeter equals to cv2.arcLength true. Okay, now what we'll do here, we'll calculate here the epsilon. So it sets the maximum allowed distance from the original curve to the simplified curve. Here it is set to 2%. We'll set it 2% of the shape's total perimeter, adjusting the smoothness factor dynamically. So we'll write here epsilon perimeter, then approximate polygon curve. So it simplifies the shape's contour line using the Douglas-Pucker algorithm, and it reduces the number of coordinates, leaving behind only the dominant vertex points. So the true specifies that the shape is a closed polygon, and here we use this. Okay. Now after that, we'll draw the approximated contour, then draws the newly simplified polygon coordinates onto the output image copy. Now approximate passes the shape as a list, and 0 tells it to draw the first and only shape inside that list. And here 0 to 55 we'll use here, that actually will specify the line color as green with a thickness of 3. If we use it here, you can see, okay, just make it 3, and after that we will print the vertex count and calculate the length of the approximate array to find out how many corner points the simplified shape has. For example, a perfect triangle prints 3 a square prints 4, a pentagon prints 5. So we'll write here print number of vertices and contour, then length approx. Then we simply just display the images. So what we'll do here, we will just do CV to show output. And okay, let's see what is it. Okay, so here you can see it detected some many shapes here actually. Here you can see it's a triangle. So there is 2, which is a simple line, then 13, then 6, 1, 2. So these are the contour vertices what we have here. Like it's a square shape, so it is 4, it is 3, like this. Okay, now let's move our next topic, which is the area measurement. So for this, make a file here. So we can just name it area.py. So we'll write here as usually. This part is same. Then right here for loop through contours, which iterates through every individual shape contour found in the image. So for count in contours, now we'll calculate the area and compute the total area enclosed within the current contour boundary. So the value is returned as the total number of pixels contained inside the shape. So right here, area equals to CV to area CNT. Then we enter print area of contour, and let's run this file. Okay, you can see the area of contours, how many pixels are there. So like this is very simple. Okay, so here some point it is 0 because this is maybe a dot point, or there is not, it is not a closed shape, maybe a line. So this is why those are zeros. Okay, now let's move our next topic, which is bounding a rectangle. So bound rectangle.py. So for this, as before, we'll just do the same. This first is always same, and then we'll use here output image copy. Then for just before like that, send contours. Then we'll calculate the bounding rectangle, computes the straight bounding rectangle that completely encloses the contours. So it returns 4 values: xy coordinates of top left corner and the width and height of the rectangle. So can we guess how it will be? That it's just simply x, y, w, h, bound rectangle. Then we'll draw the rectangle. So draws the bounding box onto the output image copy. So xy is the top left corner, and x plus w and y plus h will calculate the bottom right corner. And we'll use here the 255, which is specified the rectangle line color as blue with the thickness of 2 pixels. So we'll go here, and after that we'll just show the image and like this, and let's see what happened. So here you can see this is how we actually create the bounding rectangles. So maybe you have seen in many advanced projects that human recognition or pet recognition, where in the face of human or the pet we have this type of square. So those actually made using contours. Whenever they found human shape, though it is trained by machine learning, so then they actually draw a contour in front of that thing we desired for. Okay, now let's see the minimum enclosing circle. So let's make another new file and set minimum enclose circle .py. Okay, so the first part is same as always. Then after that, what we'll do here is copy the image, and after that, just like the way we are doing CNT and contours, so here what we'll do, we'll draw first. We will calculate the minimum enclosing circle, then finds the smallest possible circle that can be completely cover or enclose the contour. It will return the xy coordinates of the circle center as floats along with its radius as a float. So we need here three parameters, which are x, y, and then radius, like this, and then we have the center, and then radius and radius. Then we'll draw the circle. So draws the calculated minimum enclosing circle onto the output image copy center, specifies the origin point, and radius defines the size. And we will also here use the 250 whatever to specify the circle color, and then the thickness. Now let's see the images. Now let's just play the image. Now run this file. So here you can see the enclosed circles like this. Okay, so these topics are also covered. Now we'll do a simple project which will be a real life project and will help you to actually understand how actually we use contours in advanced works. So let's name the file of this project. What is going to be is we'll lively actually detect shapes through our laptop webcam. So now we are not providing a still image, we're actually going to find it using real life video right now. So for this, we'll first import CV2, then import numpy as np. Okay, now we'll write here capture equals to cv2 dot video capture. So what it will actually do, that it will open the webcam and initializes a video capture object passing 0 targets, the default built-in or connected webcam. Now first check that the webcam is open or not. So if not cap is opened, print camera cannot open the camera and exit. Okay, now what we'll do, we'll start the video. So the video will actually going through as a loop, so it will continuously running. So it runs an infinite loop to continuously capture and process the frames in real times. So right here while true, and then we'll capture one frame, then grabs the next frame from the webcam video stream, and here the rate, what it will do, that rate is a boolean indicating of if the frame was successfully read, and here frame means the raw image array containing pixel data for the specific moment. Now if I write the code, I'll start with here rate then we have frame, then we have cap.read. Okay, now what we'll do here, if not read, then break. So what it is, so if read is false, meaning the camera is disconnected or failed to read data, so it exits the loop. Okay, now we'll create a copy for drawing and makes a fresh copy of the captured frame to safely draw contours on, leaving the raw frame unaltered. So we'll write here output frame copy, then we'll convert it to the grayscale. Then to reduce noise, we'll apply here the Gaussian blur filter to smooth the image and eliminate small peaks of pixel noise. And we'll use here 5.5 kernel size, and we'll automatically do the standard deviations here. As if you have already seen my the video of, it was on blur, how we do blur, why we need that, so you already know what we are doing here. So to do this, we'll first write here blur. Okay, now we will threshold it as we have already done it many times, so it will convert to binary image, you already know that. And after that, we'll detect the contours just like we are doing. So right here, contours. Now we'll use here different mode like external. Okay, now after that we will draw it. After finding it, we'll draw it. So cv2.draw contours like this, and after that we'll show the output, and we'll also show cv. Okay, so first we'll like to show the original image, so cv2 unshow, then cv2 filters and last contours. Then we'll exit using Q. So if cv turn off, we'll use a Q. So after pressing the Q, it will break and it will release the frame and install the windows. So let's see how it actually works or not. Okay, so you can see that it's already showing the live direction. As you can see, it actually, okay, so this is the our original. Okay, so if I put it here, this is our original image, original video on live. This is after the grayscale threshold, and here you can see it's pretty much accurate when you take it close, and you can see like this. My hand already, it is nicely capturing my hand. So nice, right? With very simple codes, you can detect this my hand, and if I go like this, see, like this. If I pull something like this, it's also detecting the marker, and have something different shape, like I have a Rubik's cube here, so it's also detecting these shapes, right? Though my image quality isn't very good as I'm using the laptop webcam, if we use here some good quality camera, maybe we can get much more good result from this. And I hope you have understand how actually we use contours and how much useful the thing is. So welcome back everyone. So today we are going to start our new video, which is on color detection and real-time tracking. So topics we are going to cover is HSV color model, color masking, webcam color detection, noise filtering, real-time object tracking, mini project. Okay, so what is HSV color model? Before we start detecting colors, we need to understand why we use the HSV color model instead of RGB or BGR. OpenCV reads images in the BGR format, where every pixel contains blue, green, and red values. Although this is perfect for displaying images, it isn't ideal for detecting colors. Imagine holding a red ball under sunlight and then moving it into a dark room. In the BGR color model, all three values change significantly because brightness affects the color values. This makes reliable color detection difficult. To solve this problem, OpenCV uses the HSV color model. Now, what is HSV? So HSV stands for, here H means hue, S means saturation, and V means value. So hue, which actually represents the actual color, and saturation, which actually represents how pure the color is, and the value represents the brightness. Now, why HSV? Because lighting mainly changes the value channel. The hue remains almost constant, so detecting colors becomes much more easier. Okay, so now let's go to our terminal and see how we can convert our webcam to HSV. Okay, so now first we will starting by convert our webcam to HSV. So to do this, as usual, we'll first import the CP2. Now then, we'll capture the webcam. So as from the previous video, we have already learned this. And now, while true, red frame equals to cap red. If not red, then red. We have already know this part. How does it work? So I don't have to explain it again. Now, okay, so from this portion of this code, we already know what is happening here. So our laptop's the primary camera, which is connected to the laptop. For me, it is my webcam. So it will be open and it will capture what is in front of this camera. And now at the red comma frame, it will read one frame. And now we'll write the code to convert the HSV. Okay, so to convert it to HSV, we'll write our HSV equals to cv2 dot cvt color, then frame cv2 dot bgr to HSV. So our camera will convert from BGR to HSV. Okay, now after that we will just show, as we already know how to write this, cv2 I'm show HSV, and we can also add here the original one, which is cv2 I'm show original frame, and then if break, and we can write it here. Okay, if I run this code, you can see and now you can see that this is the original photo, original video, and this is converted HSV channel. So this is how you can convert it. And okay, so this is how we can convert this. Now let's move. So if you have noticed that the HSV image looks strange, that's because it isn't designed for humans to view directly. Instead, it stores color information in a way that makes computer vision tasks like color detection much easier. Okay, so now let's move to our next topic, which is color masking. Okay, so suppose in case of color masking, so what is it actually? So suppose we only want to detect the red objects. So we simply tell OpenCV that you keep the red and remove everything else. So this process is called color masking. So the output is a binary image. So white will be the selected color and black will be everything else. So now write the code here. So I will write here import CV2 and then import numpy and then capture video. Then okay, so now we will create a range. What are we calling the red color? So the lower red equals to, okay, so this is the color combination of for the lowest range for the red, and this is the upper red. Anything else from anything else which is not in this range of color will be black. So while true, we'll write here the red frame equals to cap red. If not red, then it will break. Then convert it to HSV scale as we have learned it before. And now we'll write here masking. So write mask equals to CV2 dot in range HSV lower upper, and then CV2 mask and original frame, and here as usual we do that. So okay, now if I run this code, okay, so in right now in my frame there is nothing red. So here you can see everything looks black. But if I bring anything red here, suppose I have this Rubiscope, you can see now it's capturing as red, and here you can see this side here is capturing as red. But if I show this side, it won't detect anything. But now it is detecting the red color. So if I have any other object like this, it's gonna also detect this. Though my camera quality isn't very good as is a laptop webcam, but if you have a very good quality camera, you can detect much more clear image. Okay. So now we'll move our next topic, which is now this okay, so okay, now we will do another little bit of change here, that we'll display only the red object instead of showing a mask. So let's show only the detected object. So how we can do that is, here we'll do a simple change, which is we'll make here the result equals to bitwise frame by frame, and we'll here use it and we'll remove this one. Okay, so now it will detect instead of just showing the mask. So and now as you can see, if I bring this, you can see it is showing the color, not white, right? Now it is showing the color. You can see that. Before doing this, we had only white. Now it's just detecting this color. So using this method, we can detect any colors from any video or anything. So if you can see this like that. Okay. Now here actually, so instead of displaying a black and white mask, here CV2 bitwise AND operation which uses the mask to keep only the selected color from the original frame. Every other pixel is removed, making the detected object easy to see. Now if we want to see any blue color, what we can do here? We will just change this range. So we'll write here 100, 150, only 50. And here keep it as it is, just 140. So now it will detect the blue colors. Now if I just write this here, you can see that my jersey color here, some blues are detecting by this. Now if I have this, you can see it's detected now blue. So any color what you want to detect, it can detect very nicely. Okay, like this. One thing I want to just tell you right now, that we have to sometimes remove noise. So sometimes you will notice small white dots appearing in the mask. So these are caused by lighting variations, reflections, or camera noise. To remove them, we'll use morphological operations. The most common technique is opening, and which removes tiny white noise while preserving the larger objects. So for this, we simply add these lines here. I'm just showing you, because after that I will going to do a simple project, then you will clear how actually we use these things. And okay, so this thing, when we use this thing here, which actually here the kernel in P1's P, P in it, we actually creates a 5x5 kernel used to examine neighboring pixels, and CV2, the disparate morphology, which performs the opening, is an erosion followed by dilation, removing isolated white pixels without significantly affecting the main object. Even after color masking, the webcam may detect tiny unwanted white noise. The morphological opening removes these small noise areas while keeping the main object intact. Okay, so now let's move to our final project, which is the real-time color tracking. Now we will use here everything what we have learned, and we'll also apply the noise removing technique here. So let's start coding. So start with import CV2 and then import numpy, and as we have used it like this, and then for right now, so now we will like to use here the blue one, so the lower blue, which is this, and we can use the upper blue like this. And if we use our kernel here, while true, then red frame goes to cap red, if not red then break, and then we can write here also HSV, we'll convert it, then we'll use the masking. Now we will remove noise from that mask image, so use this, which will help to remove the noises. And after that, we'll find the contour. As from the previous video, you know what contour is and what it actually does, so I'm not explaining it here. Okay, so what we'll do here, we'll write here if CV2, then we'll create a boundary around the our detected object. Now we'll find the center. So m equals to CV2 moments contour. Now if I will explain it now. And then okay, we'll write here text and then CV2 mask to be tracking CV2 base, and finally cap release and install Windows. Okay, so let's explain some part of this code, which is important to know. That as this thing you already understand that we have here made the range for color detection, and after that what we have here is we have created a kernel here, and what it actually does is this creates a 5x5 matrix filled with ones. So it is used for morphological operations, such as we have already told you that small noise removing. And after that we have created here loop. You already know what we have done here. Then we have converted to HSV. Then we did mask, and after that what we did here is remove noise. So here this removes small white dots caused by camera noise or reflections while keeping the main object. And after that we did contour here. So this function actually searches the binary mask for the outlines of the white objects. We have already discussed this in previous video. And contours contain the boundary points, ignores the hierarchy because we don't need it here. And also now that we have a clean binary image, OpenCV finds the boundary of every white object. Each boundary is stored as a contour. After that, what we do here, we have put it a loop, which is a for contour in contour. So there may be more than one blue object. So the process needs to be continuously run for individually, and it will, after that you can see we have put it here, the CV2 contour area is greater than 500. So it will actually ignore the very small colors or very small pixels. And after that we'll draw a boundary box. So for this we have written here the CV2 rectangle frame like this way. And after that we have drawn the rectangle, and we have to find the image moments. To do that we have inserted here the moments contour. So actually image moments are mathematical values calculated from the contours. They help us to compute properties such as area, centroid, and orientation. And for center we use here CX, this which is actually M10 divided by M00 and M01 divided by M00, where actually M00 is a proportional to the contour area, and M10 and M01 which actually the weighted sum of the x and xy coordinate, weighted sum of the x and y coordinates. So moments are actually the mathematical measurements of the contour. Using these values we can calculate the exact center of the detected object. Now after that what we have done here, that okay, so what we actually did here, y not equals to 0, because if the contour area is 0, dividing by 0 it causes an error. So this checks ensure the calculation is safe. And after that we have calculated the center, and lastly we have draw the center, and here is a put text that we have displayed the label like it's a blue object, so we have put it here. So now one thing is here, after that, okay, so here I think I should have written something here like CV to protect frame. And after that what we have done here, okay, so what I should done here, I should put a level here instead of writing dx and dy. So I will change it right now. So after frame, I'd like to write here not this. Instead, I'll write here blue object. Okay, now it's okay. And then I also instead of this, what we'll do here, I'll write here and do x comma y minus 10, and then CV2 from Harvey Simplex. Okay, these things are good, and you can just increase the okay, simply just as it is. So make it 0, and so the color will be looking good. Make it 2, and I think after that everything is almost completed. And let's see, run this project, is it good or not? Let's see. Okay, so if I bring anything blue, so it's actually detecting. And if I have something good like this, it is detecting the blue object. Even without anything AI or machine learning, you can just simply detect object using OpenCV. You can see that here it's actually detecting the object very nicely. Even though I don't have a very good quality camera in my webcam, but it's detecting very good. So any color, anything, it can detect nicely. See, even if I rotate it, it can detect this without even distorting this image. Okay, so this was the video, and I hope it helped you. Hey, welcome back everyone. Today our topic is face detection and object detection using OpenCV Python. So topics will be covered today: what is object detection, what is face detection, how cascade classifier, face detection on an image, eye detection, real-time face detection, and a final project. So what is object detection? In our previous videos, we learned how to detect colors, contours, and geometric shapes. But what if we want a computer to recognize real-world objects such as people, faces, cars, or animals? That's where object detection comes in. Object detection is one of the most important fields in computer vision. It enables a computer not only to recognize what is present in an image, but also to determine exactly where it is located. In case of image classification, it only predicts the class. For example, a dog. But in case of object detection, it predicts the dog, but also it creates a boundary box. So now we know object name, position, and size. Let's see, what is face detection? Face detection is a special type of object detection where the computer searches specially for human faces. The goal is not to identify who the person is. It only answers one question: is there a face here? If the answer is yes, OpenCV returns the coordinates of the face so we can draw a rectangle around it. Now, what is Haar cascade? This is where most tutorials simply tell you to load a classifier. We'll explain it. Before deep learning became popular, one of the fastest and most widely used face detection algorithms was the Haar cascade classifier. Even today, it is still included with OpenCV because it is lightweight, fast, and works well on CPUs. So what is a cascade? Imagine airport security. Everyone passes through the first checkpoint. Only a few candidates reach the final stage. A Haar cascade works similarly. Instead of testing every window with a complex algorithm, it quickly detects regions that definitely not our faces. So why is it called Haar? Because it uses hair-like features. These are simple black and white rectangular patterns. Suppose in eye region, the eye region is darker than the cheeks. Another example is nose. The bridge of the nose is brighter than the surrounding areas. The classifier learns thousands of these simple patterns during training. Now let's go to the terminal and see how we actually detect images in our real life. Okay, so let's start coding how we can actually detect face on an image. So first we'll start with importing the CV tool, and then we'll just write here the face cascade equals to face cascade CV2 data dot her cascade plus her cascade frontal face. Okay, so this is actually the heart of the program, and we'll do that. We'll now start the reading image. So to read the image, what we have to do here is write image equals to cv2 dot I'm read, then person code jpg. Okay, so and then we'll convert the image to the grayscale, and to do this we'll write here gray equals to cv2 color cv t color. Okay, now what will I do here is, okay, now we'll detect the faces. To do this we'll write here faces equals to face cascade multi-scale gray, where we'll write here the scale factor 1.1, mean neighbors 5, and mean size. So what actually we're doing here, that the scale factor 1.1 means the detector searches for faces at different sizes. A value of 1.1 means the image is reduced by 10% at its scale, and smaller values detect more faces but increases the processing time, and larger values are faster but may miss small faces. And the minimum neighbors 5, which actually controls how many neighbor detections are needed before accepting a face. And here okay, the lower values, it is like the more detection but not false positive, and higher values is like fewer false detection but some faces may be missed. So we ignore the object smaller than 3 by 3 pixels, and this will reduce the noises and speed up the detection. And after that we'll draw a rectangle around it. So to do this, what we'll do here, we'll just write here for faces cv2 rectangle like this. And what we'll do here after that, we'll just show the output, the detected image, so which is actually okay, okay, yes, like this. And what we'll do here, okay, and then I think here I should change enough faces and image. Okay, then what we'll do here, we'll just write here cv2 dot wait key and cv2 destroy all windows. Now if I run this, let's see if it work or not. Okay, I made a mistake here, I guess. So this would be not like that, so I have to change this, like, and if I run this now, it will work. Okay, so we can change this value here like this, 100 by 100, so that 100 by 100 pixels, anything will be ignored. So the image detection will be much more easier in this case. So if I run this, now we can see the faces has been detected. So Now let's move to our next topic. So before moving, let's go over through the code, which is we first load the pre-trained higher cascade classifier included in OpenCV. Then we read the image and converted it into the grayscale. And because the hard cascade works with intensity values instead of color information, the detect multiscale function scans the image at multiple sides and returns the coordinates of every detect faces. Finally, we loop through its detection and draw a green rectangle around it before displaying the result. So now let's make a new file. Okay, so let's go to our next topic, which is eye detector. Okay, so do this. We first write here import CV2, and then we write here eye, then cascade, then we'll write here image equals to cv2.imread, which is person.png, and after that we'll write here gray equals to cv2 color, and then write like this. So let's ignore here 2 by 2 pic, 20 by 20 pixel. Okay, we can give it 30 by 30 because I think the eyes are bigger, much more in this scale. And right here, like for in eyes, we'll same, just we'll draw a rectangle around the eyes and detect the image, red key, and CV to destroy all windows. Now, if you run this, you can see, okay, the eyes are detected, but also some of other objects looks detecting. Now to solve this problem, what we can do here, we can increase this like to 2 or 6 or 2. Okay, so let's tune this thing, and okay, so if I do this like 9, and if I increase this, you can see after increasing it's reduced. So if I give this like more value, okay, now if I go this 20 times, so now if I run this, okay, but these two are still detecting. Now what we can do here else, let's see. Okay, another one is removed. So by increasing this value, you can actually get the desired. Okay, now you can see like after giving the 50, we are getting here the perfect result. So why it is happening here? Because the neighbor means, so the neighbor actually they reduces the false detection. So much more the mean neighbor values we increase, the false detection will decrease. Now if I give here 1, you'll be able to see a lot of false detection. Now if I do this to 100, okay, now this is too much. So if I give this here 50, now it's accurate detection, right? So this is how it's work actually. You know, the eye detector work actually like the face detector. The only difference is the XML model that we loaded. The detect multiscale function scans the image at multiple sizes and returns the position of every eye. Okay, so now we have already learned this. Now what we can do, we can do a project which will give us a clear view of detecting real life eye and faces. So to do this, we'll first import CV2 and then face. So we'll try to actually identify both face and eyes in live. So to do this, we first, as we really do, then we'll also create an eye cascade, and after that we'll open our video camera, which is cap equals to cv2 dot video capture 0. Then we'll name. Okay, so the text will appear around the face. So we'll write your name equals to me. Then while true, we'll create here a loop. So what it will do actually here, okay, so it will be encapsulator. So while true, what we'll do, we'll write here rate frame, then equals to, you already know how we do this if you see my previous videos in this playlist. Now if not red, then break. So now we'll convert it to the grayscale to gray. Now we'll detect the face. So faces equals to, okay, like this. Now let's increase it to 20 and make it like 50 and 50 for a good detection. And after that, what we'll do here, okay, and then we'll go for X. So now we'll create a box. So rectangle cv2 dot rectangle frame, that rectangle frame actually X comma Y, and then I'll write it like this way. So what we'll do here, then we'll put a text here. To do this, we'll write here cv2 dot put text, and okay, after that, okay, so now we need the region of interest. So instead of searching the whole frame for eyes, we slice out the face region. This dramatically speeds up processing and minimizes random background false positives. So we'll write here a region of interest. So we'll write here ROI gray equals to gray. Okay, then so it will crop the grayscale slice for the eye detector algorithm. And then we'll write here ROI color frame. So it will also crop color slice used to draw our visual boxes. Now after that, we will write here eyes equals to eye cascade, and it will do like this, eyes equals to eye cascade dot detect multi-scale ROI gray, and we'll also add here a scale factor. So we'll throw up 30 and minimum size. Okay, it's enough, I guess. And after that, we'll move to for I'll also draw a boundary box around the each detected eye. Okay, now after that, we will do here like cv2 dot put text ROI color eyes, and after that, we will show here the I'm show. I'll write here I'm show cv2, and okay, so this will look like this. And if I run this, okay, so if I start on this, and you can see it's detected much pretty clearly my face and my eyes both together. If I cover my one full faces, you can't see anything, but whenever I move this, it's pretty much clear, right? So this is how we actually detect faces in OpenCV without using any kinds of machine learning or AI. So this was the video, and I hope you have learned a lot through this video. And I hope this playlist is going to end here, and our basics of OpenCV with Python course is completed. Hope you like this video and the playlist, so stay tuned, more is going to come, and our next series or videos will be on deep learning. I think you'll also enjoy those videos. So for today, that's enough. Ta-da.